Hi, I'm Bosun. I am currently a postdoc at the Hong Kong University of Science and Technology. Today, I'm going to present our paper, Competitive Algorithms for the Online Multiple Knapsack Problem with Application to Electric Vehicle Charging. This is a joint work with Ali and Mohammed from UMass Amherst, and Tongxin and Adam from Caltech, and Danny from HQST. In this talk, I will first introduce a general online multiple knapsack model, and then design a threshold-based algorithm that can achieve the best known competitive ratio for this model. The key novelty of this work is to propose an instance-dependent online prime-module approach that can be used to design the threshold function in the algorithm. And last, I will show the empirical performance of the proposed algorithm in real-time control of electric vehicle charging. So we consider the following problem. There are m knapsacks, each with a capacity Cm, and n atoms arrive one by one, and each atom is divisible. Upon the arrival of the nth atom, we determine the fraction of the atom assigned to each knapsack. And this assignment needs to satisfy a few constraints. First, we require that the total accepted fraction of the atom should be upper bounded by its atom size, dn. And the total fraction assigned to one knapsack should satisfy the capacity constraint. We also have a read constraint that limits at most Ynm amount fraction of the atom n can be assigned to knapsack m. So this constraint can model the heterogeneous restrictions on which atoms can be assigned to which knapsacks by setting the Ynm to 0 or a large value. So an assignment decision will generate a value which is modeled by a concave function Gn. And the goal is to determine the feasible assignments in an online manner to maximize the total value of all atoms. So formally, the problem can be formulated as a convex optimization problem. Each atom contains a piece of information that includes the atom size, the rate limits, and the value function. So the offline formulation assumes the information of all atoms is known from the start. But in the online setting, an online algorithm needs to determine the online decision just after the arrival of each atom, and can only be based on the causal information, which is the information up to the current atom n. The performance of the online algorithm is evaluated by the competitive ratio, which is the worst case ratio of the offline optimal and the online algorithm. So the online multiple knapsack model is very general. It can be considered as a general version of the one-way trading problem by extending it from a single capacity constraint problem to multiple constraint problem. It is also a generalization of the online multiple knapsack problem with small atom sizes by additional taking into account the rate limit constraints. The online knapsack can also model many practical applications. So we take the online EV charging as an example. We can make the following analogy. The knapsacks are the time slots in the EV charging problem, and the knapsack capacity models the available charging power in each time slot. And the atoms are the EVs, and the atom size models the energy demand of each EV. The rate limits capture the charging rate limit of each charger and the available charging period from the EV's arrival to its departure. So we propose to use an online threshold-based algorithm to solve this online multiple knapsack problem. The idea behind this algorithm is as follows. So we consider an offline formulation of the problem. From the dual decomposition theory, if we know the optimal dual variable corresponding to the capacity constraint, we can actually decompose the problem across the atoms, and we can get the optimal assignment solution by solving a pseudo-utility maximization problem for each atom. And this pseudo-utility is defined as the value of the atom minus a linear cost using the optimal dual variable as the price. But in online the optimal dual variables can. So the idea of the threshold-based algorithm is to estimate the dual variable as a function of the knapsack utilization. Here, this estimation function phi is called the threshold function. So the threshold-based algorithm is just to modify the cost in the pseudo-utility from a linear form to an integral. Actually, given an increasing threshold function, this integral is a convex function in the assignment decision. So the algorithm is just to solve a convex optimization problem for each atom and get the online solution. In fact, the idea of this threshold-based algorithm is not new and has been proven effective in some early works. But the application of this approach is limited because the design of the threshold function is very challenging, similar to the difficulties in designing the Lyapunov function in Lyapunov-based control. So most works just design the threshold in an ad hoc manner. The key contribution of this work is to provide a systematic way to design the threshold function. We assume the partial derivative of the value function is bounded from below and above by L and U. And we define the ratio of U over L as a fluctuation ratio theta, which is assumed to be known. So our main results say if the value functions are additionally aggregate or separable, we can design the threshold function as follows. And the corresponding competitive ratios are the solutions of these equations. So as an illustration, the blue and the red curves are the threshold functions for the aggregate and the separable value functions. And the black curve is from a design in the literature. And it actually generates an upper bound for the competitive ratios. If we look at this competitive ratio result, it's clear our design is between a 2 plus ln theta upper bound and a 1 plus ln theta lower bound. So our design is actually improving the state of the art and approaching the optimal competitive ratio because the gap between the upper and the lower bound is just 1. And here, an additional remark is that it is still an open question on how to design the threshold function for a more general value function. And it is a very interesting direction to further improve. Okay, we next show how to design the threshold function. It originates from the classical online primordial approach. we can think of the approach as searching for a threshold function phi that can satisfy the following equation for any instance. So this equation requires that the product of the competitive ratio alpha and the profit of the online algorithm is large enough and can upper bound a feasible do. And this feasible do upper bound the offline optimal based on the weak duality. So the design of the threshold function is usually transformed to figure out a set of conditions on the threshold function and the competitive ratio, such that the first inequality can hold. And we aim to design this threshold function to make the first inequality as tight as possible. But one missing point in the classical approach is that it does not carefully consider the weak duality gap, which can be pretty large for some instances. We take the generalized one-way trading as an example. So in this special case, we only have one capacity constraint. And for some under demand instances, which mean the knapsack capacity cannot be used up, even we accept all the items in the instance. So in this case, the classical primordial approach fails just because the weak duality gap is too large, and the feasible do cannot be further bounded. And the reason behind this is that the final utilization and those instances is very small, and it's actually not smaller than the capacity. So the capacity constraint in the offline problem is redundant. To fix this problem, the idea is to construct an instance-dependent offline formulation by adding some new constraints here. And this will not change the optimal offline solution. In this way, we can derive the feasible do based on this new formulation. And it will give a much tighter weak duality inequality. Using the instance-dependent approach, we can design the threshold function, and the resulting algorithms can improve the best-known compare ratios. For example, as we showed just now, in the online multiple knapsack problem, we can improve the upper bound. And in the generalized one-way trading problem, we can improve the compare ratio from a linear order in its parameter C to a logarithm order. And the improvement of our approach actually comes from an understanding of the worst case instance, because we need to construct different offline problems for different instances to reduce the duality gap. And the good point of our approach is that only even a partial understanding of the worst case instance can help improve the compare ratio. We have shown this in the analysis of the online multiple knapsack problem in the paper. Okay, finally, we apply our algorithm to the online EV charging problem and compare it with a fixed threshold algorithm denoted by FTA here. We use the empirical ratio as the performance metric, and we show the CDF of the empirical ratios from 1,800 instances. So in this CDF figure, we can see our algorithm can get a more than 40% decrease in the worst case ratio. And our algorithm outperforms the FTA for most of the instances. And although our algorithm is not designed for the average case, but if we compare the average profit ratio of the two algorithms, we still can see an over 20% of improvement of the average profit. Okay, to conclude, we have three messages in this talk. First, we introduce a general online multiple knapsack model, and we design an online algorithm that can achieve the best known compact ratios. We also propose an instance-dependent online primordial approach that can be used to design the threshold function in the algorithm. And this analysis approach has great potential to be applied in other online algorithms. Okay, this is the end. Thank you.